In this lecture, we are going to continue our discussion on group representations. In the last lecture, we defined group action on a set, and we specifically looked at the action of a group on linear vector spaces which gave rise to linear representations of groups. We also took a look at how to convert a given linear representation of a group on some vector space into a matrix representation by first choosing an ordered basis in that vector space. Of course, a question that must have arisen in your mind at that point is exactly how unique is this matrix representation for a given group. After all, the matrix representation depends directly on the choice of basis, and as you all know, there are infinitely many possible ways of choosing a basis on even a finite dimensional vector space. So even if we are talking of the same linear representation of a particular group, which means every group element is assigned a given fixed linear transformation, which obeys, of course, the group multiplication rule, even then, you could have infinitely many different matrix representations for the same linear transformation simply by changing your basis. And that is exactly what we are going to first investigate in this lecture, the notion of what is called equivalent representations. These, as you must have guessed by now, are simply different matrix representations that we can have for the same group simply by changing the underlying basis on whatever vector space you are using. And as you may well have guessed, we do not really treat equivalent representations as different representations. For all practical purposes, they are the same representation. So when we count how many representations a group has, we usually only count inequivalent representations. The infinitely many equivalent representations a given representation has, they are not really counted as separate representations. So let us start with a given basis E1, E2 up to En on a vector space capital V, and then figure out exactly how a change of basis is done. This is of course elementary linear algebra. I am just reminding you of this result. That if S is a non-singular matrix and EI prime, E1 prime, E2 prime up to En prime is connected to E1, E2, En via this relation, EI prime equals summation over j going from 1 to n, Sji Ej, then E1 prime, E2 prime up to En prime gives another ordered basis of the vector space V. And what happens to the matrix representation then? Remember, to calculate the matrix representation, what we had to do was apply the linear transformation corresponding to a group element small g on a basis vector, on the ith basis vector say, and then expand out the vector in terms of the basis vectors. So what we are doing here with this new basis E1 prime, E2 prime up to En prime is applying LG on EI prime. Of course, this is a resulting vector, and this vector can be expanded in terms of the original basis as well as in terms of the new basis. So first of all, if we connect EI prime back to EJ, the original basis vectors, that is, I am using this particular expression for EI prime. Since LG is a linear operator, it moves straight through the sum and the Sji coefficients and goes and acts on Ej. So LG Ej is what we are looking at now, and that of course can be expanded in terms of the matrix representation for G. So LG Ej is simply the sum dkj G Ek, and the sum of course runs from k equal to 1 to k equal to n. This gives us an expansion of the vector LG EI prime in terms of basis vectors, but these are the wrong basis vectors. These are the old basis vectors. What we want to do is to expand LG EI prime in terms of the new basis vectors E1 prime, E2 prime, En prime. And in order to do that, what you need to do is express Ek in terms of the E primes. And that is easily done. Since E prime is related to Ej by this, E will be related to E prime by the inverse matrix And that's all we really need. So dkj, g, sji, these are just the factors you already had. This thing in the bracket here is nothing but what ek is when you express it in terms of the primed basis vectors. And collecting everything together, you can interchange this sum over m and the finite sums over j and k, and this then becomes sum over m going from 1 to n, this whole thing in the bracket e prime m. So this thing in the bracket, of course, is now the new matrix elements for or corresponding to LG in the prime basis. This will be the mith element of the new matrix. And that, as you can easily see, is nothing but the mith element of the matrix product S inverse ds. So the upshot of all this is, when you expand LG E prime, EI prime, in terms of the prime basis vectors, you get a new matrix representing the same old LG, but this new matrix is related to the old one simply by this rule. The new matrix D prime G is S inverse dg times S. So this is exactly what linear algebra had already taught us. When you change your basis, what happens to matrices representing linear transformations is that they undergo what is called a similarity transformation. And as you all know, many things of a matrix stay unchanged when you do a similarity transformation, but it's pretty easy to understand why. After all, if you are doing a similarity transformation on a matrix, what you are really doing is you're talking about the same underlying linear transformation, but just with a change of basis. So the actually important information about the geometrical effects of the linear transformation will of course not change when you go from one matrix to another one which is similar to it, simply because they are both talking about the same linear transformation and all you have done is change your basis. What we have now is a new matrix representation corresponding to the same linear representation of the original group. So the matrices d prime g1, d prime g2, d prime g3, etc. actually furnish a matrix representation of the same group but with different matrices. Matrices different in the sense that they are related to the old matrices by this S inverse dgs, the same S of course for each of the dg's, because you are going to change your basis only once and for all. Now, just to quickly check whether this really is a representation, what we need to do is check what happens to d prime g1, g2. Of course, this check is really unnecessary because we already know that this has to be a matrix representation. After all, we have just followed the standard rules of formulating a matrix representation from a given linear representation. The only thing we have done is we have used a different basis. But still, let's check directly whether that's right. And the check follows the same method that you must have seen in linear algebra. You want S inverse dg1, g2, S, but now remember, the d's furnish a matrix representation, so dg1, g2 is dg1 times dg2. But you must all recognize the standard trick that you play here. You put in the identity in the form of S inverse in the middle of or in between dg1 and dg2. And once you do that, the first three matrices together give you d prime g1, the last three give you d prime g2. So what you have is d prime g1 g2 is d prime g1 d prime g2. What that means is this map d prime, which maps every group element to a matrix, actually is a homomorphism from the group to the set of all invertible matrices. Now, because these two representations essentially talk about the same underlying linear transformation, just with a change of basis, we call them equivalent representations. And as I have said, you do not really count them as different representations, and that is going to be very important to keep in mind when we go forward. When we say a particular group has, say, three irreducible representations, the number 3 has to be understood in this particular manner. Every irreducible representation has infinitely many equivalent representation copies. We don't count them as different. When we say 3, we are counting 3 inequivalent irreducible representations. I realize that I have not really defined what an irreducible representation is formally in this course yet. We will do that later. All I am saying is, when you count things like how many irreps a particular group has and so on, what you are doing is you are not counting equivalent representations as separate entities at all. With this slightly technical discussion out of the way, let us continue with what we were doing in the last lecture. That is, figuring out different ways of producing representations, by which I mean linear and or matrix representations of a given group. Now let us first start with the simplest possible kind of representations a group can have. The smallest representations are simply one-dimensional representations. After all, that's the smallest dimensionality a vector space can have, and so you can't go below this. Now there is one-dimensional representation which every group has, and it happens to be absolutely trivial, and so trivial that it might be surprising to note that it happens to be one of the most important representations a group may have as far as physical applications are concerned. This is called the identity. It's also known as a trivial representation, and here what happens is every group element, small g of capital G, is mapped to this matrix. Now this is a one-dimensional situation, so the matrix is a 1x1 matrix, and hence it's essentially a number, and the map which we are using is d of g for all g in capital G is simply 1. So each and every group element maps onto the same real number, namely 1, and note that this is perfectly okay as far as our definition of group representations is concerned, because what you need is that this particular defining property be obeyed. dg1 g2 has to be equal to dg1 times dg2. But by the miracle of mathematics that gives us that 1 times 1 is 1, this particular representation is always something that's going to obey dg1 g2 is dg1 times dg2. By the way, I just mentioned that this happens to be one of the most important representations for physical applications, and I'm not exaggerating. Scalars exist simply because groups have this kind of representation. Invariant objects exist because of this. I hope to make these points clearer when we start dealing with proper physical applications later on in the course. Now there is another 1D representation that you can construct out of any given matrix representation of a group, which is to replace each and every matrix that represents a group element by a corresponding number so that the multiplication rule is preserved. And we all know a number which you can map a matrix to, so that when you multiply two matrices, the corresponding number also gets multiplied. I'm sure you have all guessed what that is. That's simply the determinant. So given a matrix representation, you can always produce a 1D representation of the group capital G by just doing this. For every group element small g of capital G, you define the 1D representation d1 of G. This 1 up here within brackets is simply a reminder that this is a one-dimensional representation, and d1 of G is simply equal to determinant of dg. So every matrix in whatever matrix representation you have gets replaced by a single number. And by the property of matrix determinants, it follows that this is going to also be a representation simply because determinant of dg1 g2 is det dg1 det dg2, and that's exactly what a group representation must obey. After these two very simple representations, let us turn to something which is slightly more non-trivial. It also happens to be very, very important, especially for physics applications. This happens to be what are called function space representations. And for this, what we have to understand is that given a vector space V, there's always a linear space of functions on V. Note carefully that the curly F that we have here is a linear space of functions on the vector space capital V, not to be confused with the space of linear functions. So what do you mean by linear space of functions? Well, all you really mean by that is, let us consider the set of all functions which map vectors in the vector space to real numbers or complex numbers if you are talking about complex vector space, and you define addition of two such functions, f1 and f2, simply by demanding that f1 of v plus f2 of v is exactly what f1 plus f2 will be when it acts on v, and we define multiplication of a function f by a scalar lambda by saying lambda f is that function which when it acts on v gives you lambda times what f does to v. It's very easy to check that under this definition, the set of all functions from v to the underlying field, maybe real numbers, maybe complex numbers, constitutes a vector space. And this is the vector space we are talking about. Every element of this vector space, of course, is a map which maps a vector in capital V to either real numbers or complex numbers. Now, given a linear representation L on the group G, what that means, of course, is that for every small g in capital G, you have an operator L of G which acts on elements of the vector space to produce new vectors linearly, and more importantly, this map obeys L of G1, G2 is LG1, LG2. Given such a representation, we can use the space of functions to produce new representations. And the key towards doing that is a standard result in linear algebra. Now, this result from linear algebra that I have just mentioned is the following. Given any non-singular linear operator capital T on the vector space capital V, you can form a non-singular linear operator OT on curly F. And the way this linear operator works is that OT acts on a function f to give a new function OTF, whose result acting on a vector V is f acting on T inverse V. So this is very important and slightly counterintuitive perhaps at first sight, that in order to find the new function OTF, what you need to do is, of course, describe what OTF does to every vector in the vector space, and the rule which allows you to describe this is simply apply the original function f not on V but on T inverse acting on V. The counterintuitive thing here is, of course, the T inverse that you have put in here. The reason for that should be pretty easy for you to guess by now. This is exactly the kind of property that will help us to decide that the O corresponding to T1, T2, OT1, T2 is actually OT1 times OT2. And this T inverse ensures that, as we will soon see in the specific case of function space representations of groups. Note that this result has nothing to do with group theory per se. This, of course, talks about any non-singular linear operator capital T on a vector space V. So after this, it should be obvious how we would form a function space representation for a given group, given that you already have a linear representation for the group. All you have to do is define these function space operators capital R of G as objects which change functions f on which they act to produce new functions RGF, and this new function RGF given an argument V will produce the result which f would have produced on LG inverse V. So here LG takes the place of the operator T, and instead of this OT which corresponds to T, the notation here that we are using here is R of G, because ultimately this function space operator also depends on the group element. Now we are calling this a function space representation. What that really means is that this is a representation which is furnished by the action of the group capital G on the linear space of functions curly f. But before we are convinced that we really have a representation, what we need to check is that Rg1 G2 is really Rg1 times Rg2. To see this, we start with a function small f from curly f and two arbitrary elements G1 and G2 from capital G, and ask ourselves what exactly does Rg1 G2 do to f. And to find that out, we take this function Rg1 G2 f and apply it on V, a vector, and according to our prescription, this is the same as f acting on the linear operator Lg1 G2's inverse acting on V. Now, Lg1 G2 inverse is Lg1 Lg2's inverse, because L is a representation, so the map L is a homomorphism, and therefore it's Lg2 inverse Lg1 inverse. Now, we use this to figure out that the result that we are looking for is f acting on Lg2 inverse Lg1 inverse V, and that's Lg2 inverse acting on this vector Lg1 inverse V. So this is really the same as Rg2 f, a new function. The function f has changed to Rg2 f and it has been given an argument Lg1 inverse V. But now Lg1 inverse V is the argument given to Rg2f, and by our definition or prescription for finding out R, this is really a new function which you get when Rg1 acts on this function acting on the vector V. So that's Rg1 Rg2 acting on f, this whole function giving you this result. And since this holds for all vectors V belonging to the vector space, then Rg1 G2 acting on an arbitrary function f is Rg1 Rg2 acting on f, and from it follows, again since small f is completely arbitrary, any function belonging to curly f, that Rg1 G2 has to be Rg1 times Rg2. That is a map R which acts on small g to give you an operator acting on the function space, has the necessary properties for a homomorphism, and therefore we do have a function space representation built out of this particular homomorphism. Now in practice, when we deal with function space representations, we often do not use curly f as a space on which my operators act. Rather, we use some subspace of curly f, and typically finite dimensional subspaces of curly f, which has the advantage that they will lead to various finite dimensional representations. To see this in action, let us take an example of our old friend S3, the group of symmetries of an equilateral triangle, and let it act on a subspace of curly f R2. Here, of course, R2 is a vector space on which we already have a linear representation, and we are going to use that linear representation to figure out a representation that is going to act on curly f R2 subspace. This subspace is that of homogeneous real-valued quadratic functions. Now, any function in this space is one which maps the vector v with components x and y to the function alpha x square plus beta y square plus gamma xy, where alpha, beta and gamma are arbitrary real numbers. And it's obvious that this is spanned by the three functions which map x comma y to x square, y square and xy respectively. So this is the basis that we are going to use for our subspace, a basis in which the first basis element is x square, the second basis element is the function which maps xy to y square, the third basis element is a function which maps x comma y to xy. Now, let us make use of the representation that we have already figured out of S3 on R2 and use that to induce a representation on this subspace of homogeneous real-valued quadratic functions. Now, the first thing that we are going to look at is the identity, and of course LE of V is simply V, but what we need to remember is LE inverse, but that again is also obviously V. So under the action of LE inverse, the vector with components x and y stays with component x and y. What we are asking, of course, is what happens to the functions f1, f2, f3 under this transformation. Remember, the rule is the function gets changed to a new function, which when fed the value v will be f acting on L inverse v. So here, for this particular example, L inverse v is v itself. So it's obvious that f1, f2 and f3 do not change. So you get this mapping here. And this makes it obvious that the matrix representation, once you choose f1, f2, f3 as your basis, for this particular case is simply the identity matrix, in particular the 3x3 identity matrix. So let's look at something slightly less trivial in the next step, that for A. Now here what we again need to look at is LA inverse acting on V, but A inverse is the same as A. Remember, A is just a reflection. Doing it twice brings you back. So a reflection is its own inverse. So this is L of A inverse V, hence L of AV. Hence, this is just what happens to V under L of A. Remember, under reflection around the medial line, E1, the horizontal basis vector gets reflected to minus E1, E2 changes to E2. So what happens to the vector is it now ends up with components minus x and y. So basically, the function f1 changes to a new function, which gives you the same result that f1 would have given acting on minus x comma y. But since f1 maps x comma y to x square, it maps minus x comma y again to x square, so f1 stays exactly the same function. So does f2, but if you look at f3, if we were to feed minus x and y as arguments to f3, what it will return is minus xy, which is the negative of what f3 returns. So minus f3 is what happens to f3 when you apply this transformation. So the matrix representative of A under this transformation is simply a 3x3 matrix which has a very simple form: 1 0 0 0 1 0 0 0 minus 1. The next one takes a bit more work. You are talking of LB inverse V now. Remember, you are trying to find RB and you are asking what RBF is. For that you need to find out LB inverse V. But again, LB inverse is the same as L of B inverse, which is the same as L of B. And so L of B acting on V. Now you have to pay attention. What LB does to E1 and E2 are these two things. There is something which we worked out in the last lecture. If you have forgotten that, please look it up again. But it's easy to figure out just by using standard geometry. And therefore, what happens to the vector x comma y is that it changes to a new set of components. X becomes x plus root 3 y by 2 and y becomes root 3x minus y by 2. And now what we need to do is figure out what happens to f1 under this transformation. Of course, f1 becomes a new function out of B f1, which acting upon xy will give you f acting on this. But f acting on this is just a square of this number, which is x square by 4 plus 3y square by 4 plus root 3 xy. And that means that f1 transforms to 1/4 f1 plus 3/4 f2 plus root 3 by 2 f3. You can figure out the similar expressions for what happens to f2 and what happens to f3 under this transformation. This is pretty straightforward. It's just a matter of just sitting down and writing the things out. And now you get a 3x3 representation dB. The matrix is not really as simple as the previous two matrices. It looks like 1/4, 3/4 root 3 by 2, which goes down the first column, remember. 3/4, 1/4 minus root 3 by 2 goes down the second column. Root 3 by 4 minus root 3 by 4 half, which are these coefficients, go down the third column. Now proceeding in this way, we can easily figure out DC, which is LC inverse V is what you need to figure out. Again, the same as LCV, and straightforward calculation gives you this. Once again, let me refer you back to the last lecture for the details of what happens when LC acts on V. And therefore, this is what happens to the components X and Y, and it's a matter of straightforward algebra to figure out what happens to F1, F2, F3. And this gives rise to DC. LD's action is very similar, except that this is the first time we are seeing something which is not a self-inverse. So LD inverse V, of course L of D inverse V is the same as L of F acting on V. So this is the only thing that you have to be very careful about here. And so this is what happens to the vector. It becomes a new one with these components. You square these components to figure out what happens to F1. You square this one to find out what happens to F2. And you multiply these two to find out what happens to F3. And this is what the transformation looks like. And going along similar lines, you can easily find out what happens under small f. LF inverse acting on V is the same as LD of V. Once again, F is not its own inverse. So this is one place where you have to be careful. Straightforward application of the basic ideas will give you the fact that this is how the components change, and now you can easily figure out how the functions change. This set of 6 matrices gives us a 3x3 representation of the group S3, and the way we found this out is we started with a set of homogeneous quadratic functions on R2, used the fact that we already know what happens to R2 under the action of our group elements, and from there we went on to figure out what happens to the functions under this transformation, and that gave us this particular three-dimensional representation. It's easy to see that instead of taking this, if I had taken, say, the homogeneous 5th order functions, then that would have been spanned by x to the 5, y to the 5, x to the 4y, xy to the 4, x cube y square, x square y cube. And so it would have given me a bigger representation for the same group. And proceeding along these lines, we can find out many new representations of the same group. Now, while I hope that the proof that Rg1G2 equals Rg1 times Rg2 that I gave you a while ago, and the example of the function space representation that I've worked out just now, is enough to convince you that this is the right approach for defining a function space representation, I'm pretty sure many of you have a nagging feeling that there's something sort of strange going on here. After all, wouldn't it be better to define RGF as a function whose action on V produces the value given by F acting on LGV rather than LG inverse V? Well, it's easy to see that if you really tried out that definition, then RG1G2 would have been RG2RG1 rather than RG1RG2. And that is not what we want. There is another way in which you can think about this particular prescription, which may make it easier for you to understand what's really going on here. And for this, let us take an example of, say, a sphere, maybe the Earth itself, with some scalar function defined at all points of the sphere. Let's just say temperature at all points on the globe. Now this function can be defined, of course, in terms of some mappings of the coordinates on the points of the sphere. Now if I were to rotate the sphere, the points will turn around, carrying the temperature distribution with them. Temperature distribution now will be a new function of coordinates, not the old function, simply because the coordinates themselves have changed. The same coordinate values now refer to different points. So what will be the temperature function which describes the temperature distribution on this rotated sphere? Well, it will act on a particular vector, a position vector of a point on the sphere, by giving me the temperature which it has now, but that is the temperature which was at a point which was carried onto this particular point by the rotation. That means this used to be the temperature the original function evaluated at a point which you would have got by applying the inverse rotation on your current point. So basically what has happened is you are talking about the same temperature function, or rather same temperature distribution. The function has changed because the points have moved. So to find out the value of the function at the new point, you have to actually find out the value of your original function at the old point. That is where the LG inverse is actually coming from. I hope this makes it slightly less counterintuitive to you. We next turn to another very important kind of representation, and this is one that you can find for every group using just the basic properties of the group. This is a so-called regular representation, and this happens to be one of the most important representations which will help us in building up the theory of group representations as we go along. Now, as we have already said, in order that you get a representation of a group, the group must be acting on something. And since we are talking of linear representations, there has to be a vector space on which the group acts. But here, as I said, this particular representation depends only on the group's own structure and not on anything which you have to bring in from the outside. You might wonder, how is that possible? After all, you do need a vector space. And the answer is that somehow I can make the group itself into a vector space. Of course, the very first thing that you need in a vector space is that you should be able to add the elements. Now, in a group, you have a composition rule between the elements, but you have no separate notion of addition. A group, of course, has only one rule, which is composition of the elements or multiplication of the elements. So how do you get a vector space out of this? The answer is that a group can be converted into a vector space, curly E of G, where G is the group, by formally defining a sum of its elements and multiplication by a scalar. The scalar, of course, could be from either reals or complexes, as the case may be. Now, what does this mean? Well, let me just step back from groups a bit, ask you what may sound like a very stupid question. Can you add apples and oranges? In fact, you may very well have heard this. You can't compare apples with oranges, and so it doesn't make sense to even add them together. But think about it a bit. It does make sense to add apples and oranges. What do you get when you add an apple and an orange? You get one apple and one orange. That's it. Well, along the same lines, we can define how to add two group elements, G1 and G2, just by saying that this is defined to be G1 plus G2. And you can define multiplying a group element G by a number M by defining that, okay, there is an object called Mg in my set. And the whole idea is, if you define things this way and put in what naturally follows as the rule for combining such sums and multiplying such sums by scalars, namely, if you have something like G1 plus G2 and another element like G2 plus 2G3, their sum will be G1 plus G2 plus G2 plus 2G3, that is G1 plus 2G2 plus 2G3. So just do whatever comes naturally. Similarly, G1 plus 2G2 multiplied by 3 would be 3G1 plus 6G2. It doesn't really matter whether you can understand what 6G1 is in some separate sense or not. You don't need to. It's still a very general element of the set of all linear combinations of group elements, which we are calling curly A of G. And the symbol curly A is actually being used because this is called an algebra. A vector space which also has a group multiplication property is what is called an algebra in mathematics. Well, now that we have a vector space, it's natural to talk about a basis for the space. And given that an arbitrary element of this vector space curly A of G is going to be of the form alpha 1 G1 plus alpha 2 G2 up to alpha n Gn, where G1, G2, Gn are the group elements, and alpha 1, alpha 2, alpha n are just numbers, it's easy to see that one obvious choice of basis is just to take the group elements G1, G2, Gn. So the group elements form a natural choice for the basis of this vector space, and it is this particular vector space which we can use to define a representation. But of course, for that, what we need to figure out a way in which my group elements can act on this group algebra. So the basic idea is this. What we need to define is a homomorphism called L-reg. Reg, of course, stands for regular. This is a map which is from capital G, the group, to capital gamma of curly AG, which is a subset of the automorphism group of curly AG. This may look a bit more complicated than it really is. Remember, an automorphism of curly AG is simply an isomorphism of curly AG to curly AG. So take a general vector in this vector space and it gets mapped into another vector in this vector space. This L-reg, of course, is a mapping which maps a given element small g of the group into a particular operator, L-reg of g. This L-reg of g is going to be a member of capital gamma of curly AG, and it is going to act on a general vector in curly AG. Now, we have to define what the particular action is, and the action here is defined in this manner. L-reg g acting on V is simply defined to be V times G inverse. Now, you might ask, what exactly is a vector times a group element? What exactly does that mean? The answer is simple. All you have to think about is the vector here is some linear combination of the group elements themselves. So it's alpha 1 G1 plus alpha 2 G2 up to alpha n Gn. When you multiply that from the right by G inverse, you get alpha 1 G1 G inverse plus alpha 2 G2 G inverse plus alpha 3 G3 G inverse and so on down the line, plus alpha n Gn G inverse. And since G1 G inverse, G2 G inverse, etc. are specific group elements, you end up with some other linear combination of the group elements. That is a new vector. So this is, of course, a well-defined map from curly AG to curly AG. It acts on a vector to give you a vector in this space. The question is this a homomorphism? And of course, an associate question might very well be, why define it this way? Why define it as V times G inverse? Why not V times G? Of course, to qualify as a representation, L-reg must be a homomorphism. What that means is, L-reg acting on G1, G2 must give me L-reg G1 times L-reg G2. In order to see whether this is true, what we can do, of course, is take L-reg G1, G2 and apply it on an arbitrary vector, small v, belonging to curly A of G, that is the group algebra of the group G. Now, by our rule, what this gives is V times G1, G2 inverse. And because G1, G2 inverse is G2 inverse, G1 inverse, this of course is V G2 inverse multiplied from the right by G1 inverse. Now, once again, our rule for the action of the regular representation simply tells us that this is L-reg G1 acting on the vector V G2 inverse. But now let us look at the argument on which L-reg G1 is acting. V G2 inverse is a vector which can be obtained by applying L-reg G2 on V. So this is really L-reg G1 acting on L-reg G2 on V. What that means is, of course, this is L-reg G1 G2 is the same as L-reg G1 L-reg G2. Remember, this is a map, so when we say multiplication, we mean composition, and in this case, L-reg G1 L-reg G2 means L-reg G1 gets to act after L-reg G2 acts. And since this happens for arbitrary V, we must conclude that L-reg G1 G2 has to be the same as L-reg G1 times L-reg G2. And thus, L-reg is a homomorphism. And so, we do have a group representation on this vector space which is furnished by the group itself, or which we have made the group into. Now, in case you were wondering, instead of using Vg inverse as the rule for L-reg G acting on V, if we had actually started by saying Lreg G acting on V would give me Vg, then Lreg G1 G2 would not turn out to be Lreg G1 times Lreg G2. I would have got Lreg G1 G2 equals Lreg G2 Lreg G1. And because of this reversal in order in the product, this does not qualify as a homomorphism. This is of course why you don't define Lreg G acting on V as V times G. We define it as V times G inverse. Again, in case you are wondering, does it have to be a right multiplication? Why can't I define the regular representation by saying Lreg G acting on V will give me G times V? Indeed, the map L tilde reg, which maps a group element small g of capital G to what actually is a map L tilde reg G. Remember, L tilde reg G belongs to the automorphism group of curly AG of the group algebra, which means L tilde reg G is a map which acts on group algebra elements to produce new group algebra elements. Now this particular map L tilde reg G, which acts on small v, a group algebra element, by producing G times small v, turns out to be a homomorphism too. And so there is no real reason why you have to define Lreg G by Lreg G acting on V is Vg inverse. I could have also defined it by demanding that Lreg G acting on V gives you G times V. In fact, some authors do use this second definition of the regular representation. We will of course stick to whatever definition we have started with. However, you have to be aware that the other definition is also very much in use. In which case, you might of course ask the question, which one of the two is the actual regular representation? After all, if the regular representation is so important, there should be a unique definition for that. As it turns out, these two representations happen to be equivalent to each other. And because of that, we should not really need to distinguish between them. They are effectively the same representation and they will look different, for example, but that's more because of a different choice of basis than anything else. Let us now turn to the question of the matrix representation corresponding to our regular representation. Of course, each and every one of the group elements, small g1, small g2, etc., get mapped under this regular representation to a linear transformation acting on the group algebra. And to find out the corresponding matrix, what we need to do is to figure out what Lreg Gi, a specific linear transformation, does when it acts on the basis of curly AG. Now, as I said, one of the obvious choices for the basis of curly AG are nothing other than the group elements themselves, that is G1, G2, G3 and so on. So we are asking ourselves, what does Lreg Gi do to an element Gj? And we know that our rule simply says Gj times Gi inverse is exactly what is going to come out. Now note that Gj and Gi both being group elements, Gj times Gi inverse is a specific element of the group. However, going by the fact that this is a vector space now, and you can expand any element of the vector space in the basis that you have chosen, namely in G1, G2, Gn, we can of course write down the matrix corresponding to Lreg Gi, dreg Gi, as one whose kjth element is defined like this. You have to sum over all k, running of course from 1 to the order of the group, of dkj regular corresponding to Gi times gk. Now, of course, since this term is just one of the group elements, that is one of the basis elements, exactly one term here will be equal to 1 and the others will all be 0. So, for a fixed j, that is for a fixed column of this regular representation matrix, in fact, this is not just one regular representation matrix, but every one of the regular representation matrices that we have, they will have this one property, that in each column you will have exactly one element which is 1 and all the other elements will be 0. In fact, this works not only for every column, you can easily figure out that this also works for every row. And this essentially tells you that dkj regular of gi is simply 1 if gk inverse gj is gi, otherwise it's 0. Of course, note that if this will be 1 if gk happens to be gj gi inverse, and gk equal to gj gi inverse can of course be written in terms of the indices k and j by rewriting that as gk inverse gj equals gi. And that is the only term which is going to give you 1, all the others are going to give you 0. Now this tells us that the regular representation matrices corresponding to each one of the group elements can be read off directly from the group multiplication table itself. And this is what I am going to describe next. To illustrate the process of writing down the matrix elements representing the regular representation of any group, we will fall back on our old friend, the one example which we keep on using over and over again, the group of symmetries of the equilateral triangle. Let me just remind you that we had already figured out its multiplication table, and the multiplication table turned out to be this one. Now what we are going to do is we are going to simply rewrite the multiplication table slightly differently. In a standard way of writing down the multiplication table, each column is represented, of course, by one group element, and each row is labeled by a group element, and these are put in exactly the same order. That is, you have E, A, B, C, D, F as a label for these columns, and you also have E, A, B, C, D, F as a labels for these rows. However, our defining property of the regular representation matrices, which is dkj gi is 1 if gk inverse gj is gi, otherwise it's 0, that suggests a very nice way of rewriting the multiplication table, which will make reading of the regular representation matrices trivial. And there what we have to do is simply write down the multiplication table with a small change. Instead of E, A, B, C, D, F labeling both the columns and the rows, we will label the column by the group elements taken in whatever order. In this case, we have been using the order E, A, B, C, D, F. But the rows will be labeled in the same order, not by the group elements directly, but by the inverse group elements. So instead of E, A, B, C, D, F, the labels here will be E inverse, A inverse, B inverse, C inverse, D inverse, F inverse. I'm not sure whether you have noticed this, but there has been a change in the multiplication table because of this. If you focus on the last two rows here, they have been swapped. This, of course, is simply because in this particular group, the elements E, A, B and C are their own inverses, so the rows corresponding to them have not changed. D and F, on the other hand, are inverses of each other, so they will get swapped when you replace D by D inverse and F by F inverse. So what we end up with is this new way of writing down the multiplication table. Essentially the same table, just with a rearrangement of the rows. But now it becomes very easy to read off the representation matrices. If you want to find the representation matrix of a particular element, let's say B, all you have to do is figure out something like this. For example, here you have a B here. What does it mean? It means E inverse times B is B. You have a B here, that means A inverse times D is B. And if you just remember the rule that we had, that is this rule, gk inverse gj being equal to gi, then you will have the kjth element to be 1 and otherwise 0. That immediately tells me that in this way of writing down the multiplication table, if I want, say, the regular representation matrix for the element B, then all I have to do is find where are the B's in this table and replace all the B's by 1s and replace all the other elements by 0, and I've got the representation matrix. To show that in action, let's go do these elements one at a time. The element E, of course, must have the identity matrix as the representation matrix, and that is obvious here. If you look at where the E's are in this version of the multiplication table, they're just down the diagonal. And so you can immediately read out D regular of E as this 6 by 6 identity matrix. Of course, there's nothing very special about that. That's sort of obvious. However, how would you find out D regular of A? All you have to do is identify where the A's are in this table and replace those positions by 1 in the corresponding matrix. So you have 2 1s A's here and 4 A's along the line, 4 1s here, 2 1s. All the others are replaced by 0. That's your regular representation matrix for A. B, well, very similar. You can just immediately read off what the matrix is. C, this is what the matrix is. A 1 C here, a C here in the table means a 1 here and a 1 here. After 3 zeros horizontally, 3 zeros vertically, and so on. 1 here, 1 here. These 4 C's give you 4 1s in these 4 columns. Running through this quickly, D regular for D, again, just identify where the D's are. You get, again, 6 1s in 6 of the columns. And identifying where the 1s are is exactly what this rule does for you. And this is the regular representation matrix for F. At this point, I will draw your attention to a very important observation. Why this is so important will be clear when we talk about characters later. But let me just point out the observation at this stage anyway. It is obvious that the identity will be represented by the identity matrix. The number of rows and columns of the matrix will of course be the number of elements in the group G, because that's exactly the dimensionality of the group algebra. Other than the identity, the representation matrices for all of the other group elements will not have a single non-zero number on the diagonal. Which means if you look at the trace of the matrices, the identity matrix which corresponds to the identity element will have a trace which is obviously equal to the order of the group. The trace of all the other representative matrices will be 0. Now, as you will see later, trace of the matrices in a representation happens to be a very important property which can actually tell you a lot about the representation. And in this particular case, this result for the regular representation, that the trace for the identity matrix or the matrix corresponding to the identity is order of the group and all other traces are 0, happens to be a very important piece of information. But all that will have to wait for a later lecture. Bye for now.